The cosmos is racing apart faster every second. This relentless acceleration is one of the greatest mysteries in all of science, and its explanation will redefine our place in the universe. By the end of this journey, you will understand 30 of the most compelling theories physicists have conceived to explain this infinite expansion. We will explore how empty space itself might possess a repulsive force, and whether our entire universe is just one bubble in an endless cosmic foam. What single idea about the universe's fate intrigues you the most? Einstein introduced a fudge factor into his equations of gravity, a mathematical term he called the cosmological constant. He originally added it to keep the universe static and unchanging, a notion he later dismissed as his greatest blunder. Yet this very idea has made a spectacular comeback. The cosmological constant is now the leading explanation for the universe's accelerating expansion. It represents a uniform energy density inherent to the vacuum of space itself. Think of empty space not as a true void, but as a seething field of energy that exerts a gentle, persistent push on the cosmos. This repulsive force is incredibly weak, but because it is a property of space, its influence grows as the universe expands and creates more space. This concept is the cornerstone of the lambda-CDM model, the standard model of our cosmos that successfully explains a vast range of observations, from the afterglow of the Big Bang to the way distant supernova appear dimmer than expected. But this triumphant solution comes with a profound and embarrassing problem. When physicists try to calculate the value of this energy from fundamental theory, the number they get is astronomically large, about 120 orders of magnitude stronger than what we actually observe. This is not a small error, it is the worst prediction in the entire history of science. So the mystery deepens. Why is the push of empty space so inexplicably feeble, yet precisely tuned to allow galaxies and life to form? The answer might lie not in the force itself, but in the very fabric of reality. This embarrassing mismatch between prediction and reality forces us to ask if dark energy is truly constant. What if the force driving cosmic acceleration is not a fixed feature of the vacuum, but something that evolves? This is the compelling idea behind Quintessence, a dynamic and shifting form of dark energy. Unlike the stubborn, unchanging cosmological constant, Quintessence is a theoretical scalar field that permeates all of space. Think of it not as a static energy, but as a kind of cosmic weather that can change in pressure and density over time. This fluid-like quality allows it to either accelerate the universe's expansion more forcefully or to ease off, offering a potential explanation for why the expansion rate might not be locked into a single, relentless gear. Some models of Quintessence even predict a future so violent it makes the Big Freeze seem tranquil. In a scenario called the Big Rip, this field could grow so powerful that it overcomes every force holding things together. First, it would shred galaxy clusters, then individual galaxies. Stars would be torn from their systems, planets from their stars. In the final moments, atoms themselves would be ripped apart, dismantling the very fabric of reality. This terrifying potential highlights the key difference. The cosmological constant is a steady push, while Quintessence is a force that can learn and adapt. This flexibility is precisely why many cosmologists are drawn to it. A dynamic field can better fit certain observational quirks and might solve the profound fine-tuning problem, suggesting the universe's acceleration is not a cosmic coincidence, but a changing chapter in an ongoing story. But the story of dark energy grows even stranger. Beyond the steady push of the cosmological constant and the shifting nature of Quintessence lies a third, truly terrifying possibility. Phantom energy is a hypothetical form of dark energy so potent and so bizarre that its equation of state allows for a negative pressure with a vengeance. Think of it as a cosmic force that does not just push the universe apart, but actively strengthens itself as it expands. This creates a runaway feedback loop of acceleration. With phantom energy, the repulsive gravity does not remain constant or slowly change. It grows infinitely more powerful over time. The ultimate consequence of this self-amplifying push is a cosmic doomsday known as the Big Rip. In this scenario, the expansion rate does not just increase, it skyrockets to an unimaginable intensity. First, the phantom energy would overcome the gravitational glue holding entire galaxy clusters together, sending them flying apart into the void. Then, individual galaxies would be shredded. Next, the force would tear through our own solar system, pulling planets away from their stars. As the end draws near, Earth itself would be ripped apart. Mountains would be flung into space. Finally, in the last fleeting moments, the bonds between atoms would be severed, and the very fabric of space-time would be torn asunder. The universe would end not with a freeze or a crunch, but with a violent, fundamental disintegration of everything that exists. While phantom energy is not the leading candidate to explain our observations, it remains a mathematical possibility that fits within certain cosmological models. Its profound implication is that the vacuum of space could harbor a latent power far more destructive than we have ever dared to imagine, a hidden force waiting for its moment to unravel reality itself. What if dark matter and dark energy are not two separate mysteries, but two faces of the same cosmic entity? This is the radical proposition of the Chaplygin gas, a single exotic fluid that could unify the two greatest puzzles in modern cosmology. Imagine a strange substance that behaves one way under the dense, crowded conditions of the early universe, but completely transforms its character as the cosmos expands and thins out. In the beginning, this fluid would have acted just like dark matter, clumping together under gravity to provide the scaffolding for galaxies and galaxy clusters to form. It was the invisible architect of cosmic structure, but as the universe grew older and more spacious, this same fluid underwent a profound metamorphosis. It began to resist gravity, developing a powerful negative pressure that started pushing the universe apart. In its later life, it became indistinguishable from dark energy, driving the accelerated expansion we observe today. The mathematical heart of this idea is a specific equation of state, a unique relationship between the fluid's pressure and density. This formulation allows it to seamlessly shift from a clustering, matter-like state to a smooth, energy-like state over billions of years. The appeal is immense. It offers an elegant simplification, solving two of the universe's biggest mysteries with one elegant, unified component. It paints a picture of a cosmos governed by a single, evolving substance. Yet for all its theoretical beauty, the Chaplygin gas model faces serious challenges. Its predictions for how structures form in the universe, the specific patterns of galaxy clustering, and the details of the cosmic microwave background do not perfectly match what our telescopes actually see. The universe, it seems, might be more complex than a single fluid can explain. This forces us to look for an even deeper answer, one that might lie not in a new substance, but in a fundamental flaw in our understanding of gravity itself. Perhaps our entire search for dark energy is a colossal misdirection. The real problem might not be a mysterious substance pushing the universe apart, but a fundamental flaw in our understanding of gravity itself. This is the radical argument behind modified Newtonian dynamics, or MOND. It proposes that Isaac Newton's famous laws and even Einstein's refinements break down under certain cosmic conditions. Specifically, in the realm of extremely weak gravitational fields, like those found in the vast outskirts of galaxies, gravity might behave differently than our textbooks claim. The primary evidence for this idea comes from the way galaxies spin. According to Newtonian physics, stars on the outer edges of a spiral galaxy should move much slower than those near the center, just as Pluto orbits the Sun more slowly than Earth. But observations show this is not true. Stars in the galactic suburbs orbit just as fast as those downtown. The standard solution is to invent dark matter, an invisible halo of matter that provides the extra gravity to hold these fast-moving stars in place. MOND offers a stunningly simple alternative. It suggests that at these very low accelerations, the force of gravity does not fade with the square of the distance as expected, but instead follows a different rule. With this single tweak, the theory can perfectly explain the rotation curves of hundreds of galaxies without needing a single particle of dark matter. The success is undeniable and deeply challenging to the mainstream view. But if MOND is to be a complete theory, it must also explain the universe's accelerating expansion without resorting to dark energy. This led to the development of relativistic versions of the theory, like tensor vector scalar gravity or TVS. These more complex frameworks attempt to rewrite Einstein's general relativity to account for cosmic acceleration as a pure gravitational effect, a consequence of the modified laws playing out on the largest scales. The result is a scientific war between two vastly different worldviews. On one side, the standard model with its two invisible pillars, dark matter and dark energy. On the other, MOND and its descendants, which seek to explain the same cosmic anomalies by altering the one force we thought we understood. The debate is fierce, fought over key observational tests. Can MOND explain the precise details of the cosmic microwave background, the afterglow of the Big Bang? Can it account for the gravitational lensing we see in massive galaxy clusters? For now, the consensus holds that the standard model, for all its mysterious components, provides a more complete fit to the full suite of data. Yet MOND's persistent successes at the galactic scale are a constant, nagging reminder that our grasp of gravity may not be as final as we once believed. If the very rules of attraction are wrong, then what other cosmic secrets have we been misreading all along? This war over gravity's true nature forces us to question the very stage upon which the drama unfolds. What if our three-dimensional universe, with all its galaxies and forces, is nothing more than a magnificent illusion? The holographic principle, a staggering idea born from the clash of general relativity and quantum mechanics, suggests exactly that. It proposes that our reality is a projection, a hologram. All the information that makes up everything you see and experience, every star and every person, might actually be encoded on a distant, two-dimensional surface that surrounds us. Think of it like a bank security hologram on your credit card. The flat, shiny surface contains all the data needed to generate a shimmering, three-dimensional image. In the same way, our cosmos could be a vast, complex projection from the edge of space. This is not just a metaphor. The mathematics of black holes shows that the maximum amount of information or entropy a region of space can contain is not proportional to its volume, but to the area of its boundary. It is as if the universe has a fundamental pixel size, and the number of pixels is limited by the surface area of the cosmic sphere. So how does this connect to dark energy and the universe's expansion? The energy content of the universe is tied to its information content. In a holographic cosmos, the dark energy we observe could be a natural consequence of this information limit. It would not be a mysterious substance, but a thermodynamic force, an effect of the universe hitting its maximum data storage capacity. The push of expansion might be the cosmos' way of managing its information budget. Applying this principle to cosmology leads to radically different predictions for our ultimate fate. The standard model, with its constant dark energy, often points toward a slow, cold big freeze. But a holographic universe might avoid this lonely end. Some models suggest the acceleration could naturally slow down or even reverse as the cosmic information budget is recalibrated. The universe would not tear itself apart or fade into emptiness, but could potentially cycle or find a stable equilibrium. This idea reframes the greatest mystery of our time. The force accelerating the cosmos may not be a ghost in the machine, but a fundamental feature of reality's code, a projection so perfect we are living inside it. Our cosmic code, the very laws of physics, feel fixed and absolute. But what if they are merely local bylaws? The theory of eternal inflation suggests our entire universe is just one bubble in an endless, frothing sea of reality. Picture a vast meta-universe, a background of space-time that is inflating at an unimaginable rate, faster than the speed of light. Within this chaotic, expanding foam, random quantum fluctuations can cause tiny patches to stop inflating. Each of these patches becomes a separate bubble universe, nucleating like a crystal in a supercooled liquid. Our Big Bang was not the beginning of everything, but simply the moment our particular pocket of reality stopped inflating and began the slower, more familiar expansion we observe today. The staggering implication is that this process is eternal, constantly creating new bubble universes, each with its own random set of physical constants. The strength of the nuclear forces, the mass of an electron, and crucially, the amount of dark energy are all determined by a cosmic lottery. In most of these bubbles, the dark energy value is probably enormous. In such a universe, the repulsive push is so strong that space expands violently fast, ripping apart any potential for galaxies, stars, or planets to ever form. It is a sterile, empty cosmos, but by pure chance, a few bubbles will have a very small value for dark energy. We, of course, find ourselves in one of those rare, hospitable pockets. This is the anthropic argument. The reason we measure such a feeble, finely tuned dark energy is not due to any fundamental law, but simply because we could not exist in a universe where it was any stronger. This idea offers a neat, if humbling, solution to the fine-tuning problem. We are not special, we are just lucky. Yet this grand vision of a multiverse faces a major criticism. If these other universes are permanently disconnected from our own, forever beyond the horizon of our observable cosmos, how can we ever prove they exist? The theory struggles to make testable predictions that could confirm or deny it. Some physicists argue this moves the idea from science into the realm of philosophy. They ask, is a theory that explains everything but predicts nothing truly scientific? Proponents counter that we might find indirect evidence, perhaps imprinted on the cosmic microwave background from a long-ago collision with another bubble. For now, the multiverse remains a breathtaking possibility, one that redefines our cosmos from a single entity into a single page of an infinite book. But the idea of an eternal multiverse is not the only vision of a cosmos without end. Another profound theory offers a different kind of infinity, one that is not spatial but temporal. The cyclic model suggests our universe has no true beginning and no final end. Instead, it undergoes an endless cosmic dance of expansion, contraction, and glorious rebirth. In this view, the Big Bang was not a singular creation event, but simply the most recent turning point in an infinite series. One of the most compelling versions of this model involves our universe existing as a three-dimensional membrane or brain, floating within a higher dimensional reality. Picture our entire cosmos as a single, vast sheet. Now imagine another such sheet, a parallel universe, hovering a microscopic distance away in a hidden dimension. These two brains could be drawn together by gravity, periodically colliding. Each collision would release an unimaginable firestorm of energy, which we would experience as a Big Bang. The universe would then expand from that point, just as ours has, until the energy from the collision dissipates and the gravitational attraction pulls the brains together once more, beginning the cycle anew. This elegant idea cleverly avoids the troubling singularity of the standard Big Bang, that point of infinite density where our known laws of physics break down. The Big Bang is redefined not as a creation from nothing, but as a transformative collision. This is where dark energy plays its most crucial role. In the cyclic model, dark energy is not a force leading to a cold, lonely death. It is the cosmic janitor that prepares the universe for its next act. As the universe expands and accelerates due to dark energy, it becomes incredibly vast, empty, and smooth. It dilutes all matter and radiation, wiping the cosmic slate clean. This process of dilution is essential. It ensures that when the next collision occurs and a new cycle begins, the universe starts with a clean, uniform state, ready for new galaxies and stars to form without being cluttered by the ashes of the previous cycle. This stands in stark contrast to the standard Big Bang model, which paints our cosmos as a one-time event on a one-way journey to oblivion. The cyclic model offers a grander, more philosophical narrative. It implies that time itself is circular, not linear. Every ending is merely a prelude to a new beginning. The implications are humbling and awe-inspiring. The same laws of physics, the same particles, and perhaps even the same forms of life may have arisen countless times before in cycles without number, and may do so again for all eternity. It is a universe that truly lives forever, not by persisting, but by perpetually renewing itself. This vision of a cyclic cosmos finds its most detailed form in the Ekpyrotic universe. Here, the grand dance of creation and destruction is choreographed by the hidden dimensions of string theory. Our entire three-dimensional reality is a membrane, a brain, existing within a higher dimensional space called the bulk. A parallel universe, another brain, floats silently alongside our own, separated by a gap almost unimaginably small. Gravity, leaking between dimensions, slowly draws these two cosmic sheets together. They do not collide head-on, but instead approach each other in a slow, glancing blow. This contact is not a violent crash, but a process of annihilation and conversion. When the brains meet, the kinetic energy of their motion is transformed instantly into a searing, dense fireball of radiation and matter. This is our Big Bang, not a singular point of infinite density, but the result of a transformative collision in a higher dimensional reality. This elegant mechanism provides a stunningly simple answer to one of the universe's oldest puzzles, its profound uniformity. Why does the cosmic microwave background, the remnant heat from the early universe, look almost exactly the same in every direction we look? The inflationary theory solves this by having the universe expand faster than light, smoothing everything out. The Ekpyrotic model offers a different path. Because the colliding brains are flat, parallel sheets, their interaction is smooth and uniform across their entire vast surface. The energy of the collision is released evenly everywhere at once, naturally creating the homogeneous, uniform cosmos we observe without needing a period of hyper-fast inflation. This fundamental difference leads to a clear, testable prediction that could one day settle the debate. Inflationary models generically predict a background of primordial gravitational waves, ripples in spacetime from its explosive birth, which should leave a distinct curling pattern in the cosmic microwave background. The Ekpyrotic scenario, however, produces these waves much less efficiently. The slow, grinding collision of the brains creates a far weaker signal. If future telescopes detect this specific signature of primordial gravitational waves, it would be a monumental victory for inflation. But if they continue to search and find nothing, the silence of the cosmos would speak volumes, pointing toward a cyclic universe born from a collision of worlds we cannot see. The fate of our cosmos, it seems, may be written in waves we have only just begun to learn how to read. Perhaps the very constant we hold most sacred is not so constant after all. The speed of light is the ultimate cosmic speed limit, a fundamental pillar of modern physics. But some theorists propose a truly radical idea that in the searing heat of the newborn universe, light traveled much, much faster. This is the core of variable speed of light, or VSL, theories. If the speed of light has been steadily decreasing over billions of years, this single change could solve multiple cosmic puzzles at once. In the standard model, the universe required a brief period of hyper-fast inflation to explain its uniformity. A faster speed of light in the early universe could have achieved the same result. Information carried by light could have crossed the cosmos in an instant, allowing distant regions to even out their temperature and density, creating the smooth universe we see today. Furthermore, a slowing speed of light could mimic the effects of dark energy. As light's velocity changes, it alters the way we interpret the expansion history of the universe. The observed dimming of distant supernovae, our primary evidence for cosmic acceleration, might not be due to a repulsive force, but simply a consequence of light having moved faster in the past when those stars exploded. This would be an illusion on a cosmic scale, a trick of the changing constants. Pioneers like physicist Joe Megiddo have developed detailed mathematical frameworks for this idea, creating self-consistent models where the laws of physics evolve. Yet for all its elegant problem-solving, VSL theory faces monumental challenges. The entire theory of relativity is built upon the foundation of a constant speed of light. Change that one rule, and the elegant structure of space and time as a unified fabric begins to unravel. Many of the most cherished results in modern cosmology depend entirely on light's constancy. Without it, we lose a reliable yardstick for measuring the universe. To date, there is no direct experimental evidence that the speed of light has changed. Every test we have conducted, from laboratory experiments to observations of distant quasars, confirms that it remains the same unwavering constant. So why even entertain such a heretical idea? Because the existence of dark energy is equally strange. VSL theories represent a profound philosophical choice, a willingness to question our most basic assumptions about reality itself. If the rules of the game can change over time, then the entire history of the cosmos might be written in a language we are only just beginning to decipher. The quantum realm reveals a universe far stranger than it appears. According to quantum field theory, what we perceive as empty space is not a true void. It is a seething, bubbling cauldron of activity. At the tiniest scales, pairs of virtual particles and their antiparticles are constantly flickering into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This endless, frenetic dance of creation and destruction is not just theoretical. Its effects are measurable in the lab, subtly shifting the energy levels of atoms in a phenomenon known as the Lamb shift. The collective energy of all these fleeting virtual particles, the zero-point energy of the vacuum, should be immense. This sea of quantum noise is the most natural candidate for the source of the cosmological constant, the energy imbuing empty space with its repulsive push. Yet this elegant idea leads directly to the most embarrassing calculation in all of modern physics. When theorists attempt to sum up all the potential contributions from every known quantum field, the result is a number so catastrophically large it defies comprehension. The predicted vacuum energy density should be about 10 to the power of 120 times greater than the value we actually observe from the universe's accelerating expansion. This is not a small rounding error. It is a discrepancy so vast that it represents a fundamental crisis in our understanding. If the quantum vacuum held the energy we calculate, the repulsive force would have been so unimaginably powerful that the universe would have been ripped apart in the first instant of the Big Bang, before any star, galaxy, or atom could ever form. The fact that we exist to ponder this problem means the true value is almost exactly zero, a cancellation of almost perfect precision. This vacuum catastrophe stands as a stark warning, a sign that we are missing something profound, perhaps a deeper symmetry in nature or a connection to a theory that seamlessly unites the quantum world with the force of gravity. This staggering mismatch between calculation and reality is known as the cosmological constant problem, and it is arguably the most severe disconnect in all of theoretical physics. The vacuum energy we predict from quantum mechanics is a staggering 10 to the power of 120 times larger than the tiny amount we actually observe. To grasp the scale of this error, imagine predicting that a single grain of sand should weigh as much as our entire observable universe. The number is so wrong it is not even wrong. It signals a complete breakdown in our understanding. This is not a simple math error to be corrected. It points to a fundamental chasm between our two most successful theories, quantum mechanics and general relativity. One governs the impossibly small, the other the immensely large, and they refuse to speak the same language when it comes to the energy of nothingness itself. So how do physicists attempt to bridge this chasm? One elegant proposal is supersymmetry. This theory posits that for every known particle of matter, like an electron or a quark, there exists a superpartner, a force-carrying particle. For every force particle, like a photon, there is a superpartner matter particle. This beautiful symmetry, if unbroken, would mean the positive energy contributions from ordinary particles and the negative energy contributions from their superpartners would perfectly cancel out, resulting in a vacuum energy of zero. The problem is, we see no evidence of these superpartners in our particle colliders. If supersymmetry exists in nature, it must be a broken symmetry, meaning the partner particles are too heavy for us to detect. And a broken symmetry ruins the perfect cancellation, leaving behind a small, but still far too large remnant of vacuum energy. Another, more philosophical solution is the anthropic landscape of the multiverse. In this view, the cosmological constant is not determined by a fundamental law, but is a random variable that takes on different values in different pocket universes. In the overwhelming majority of these universes, the value is enormous, and the universe expands so rapidly that no stars or planets can ever form. We, of course, find ourselves in one of the exceptionally rare bubbles where the value is minuscule, simply because such a universe is the only kind that can support life. This offers an explanation, but it feels to many like a surrender, replacing a physical mechanism with a statistical accident. Ultimately, the cosmological constant problem is a glaring signpost. It tells us that our current picture of reality is profoundly incomplete, that we are missing a crucial piece of the puzzle that unites the quantum world with the cosmos. Solving it will require a revolution, one that rewrites the rules of spacetime itself. The universe's accelerating expansion points toward a final state of profound and permanent silence. If dark energy remains a steady, unchanging force, the cosmos is destined for a fate known as the heat death or the big freeze. Picture the distant future, trillions of years from now. The last stars have long since flickered out, their fuel exhausted. Galaxies stretched beyond recognition by the relentless expansion have faded from view, their light too red and faint to ever reach another. All that remains are the corpses of stars, black holes, and drifting planets, all cooling toward absolute zero. But even this is not the end. Over timescales so vast they dwarf the current age of the universe, even these remnants will decay. Black holes, once thought to be eternal, will slowly leak their mass away through Hawking radiation, eventually vanishing in a final, faint puff of particles. Protons, the very building blocks of atomic nuclei, may themselves be unstable, decaying over eons into pure radiation. The final act of our universe is not a dramatic explosion, but a slow, irreversible fade. The cosmos becomes a near-perfect vacuum, an unimaginably vast and ever-expanding void, where the temperature uniformly approaches absolute zero, and no energy remains to power any process, any thought, or any light. This is the ultimate triumph of entropy, where the universe achieves a state of maximum disorder and stillness. It is a future of infinite space and infinite time, but devoid of all change, all structure, and all story. This chilling scenario is the most widely accepted fate if the cosmological constant is truly constant. It is the ultimate conclusion of a cosmos driven by a relentless, gentle push into an eternal, silent night. The Big Rip is a timeline of cosmic demolition so precise it feels almost scripted. If the phantom energy driving this scenario is real, its power does not just grow, it accelerates. The countdown to oblivion would begin in earnest roughly 60 million years before the end. first to go would be the largest structures in the universe. The phantom energy's repulsive force would overcome the gravitational pull binding entire clusters of galaxies together. These vast cities of stars, each containing thousands of galaxies, would be violently flung apart into the ever-expanding darkness. About 60 million years later, with the end just months away, the same fate would befall individual galaxies. The Milky Way itself would be torn asunder, its stars scattered like dust in a hurricane. The destruction would then race inward. In the final minutes, the phantom energy's grip would reach our solar system. Its repulsive force would exceed the sun's gravitational hold. Planets would be ripped from their orbits, hurled into the freezing, empty void. Earth would be shattered into fragments. Moments before the end, the very fabric of matter would unravel. The forces holding molecules together would be defeated. Mountains, rocks, and even your own body would disintegrate into a cloud of disconnected atoms. In the last infinitesimal fraction of a second, atoms themselves would be torn apart, their nuclei and electrons separated. Finally, space-time itself would be shredded, dissolving the fundamental building blocks of reality into nothing. This is not a freeze or a crunch, but a total and violent disintegration. For this terrifying future to become our most likely destiny, a single key observation would need to change. The phantom energy model requires that the equation of state parameter, a number physicists call W, must be less than -1. Our current best measurements from supernova and the cosmic microwave background peg W at very close to -1, the value for a simple cosmological constant. The universe, for now, seems to be holding back from that self-amplifying brink. If future observations were to definitively measure W dipping even slightly below that magical threshold of -1, the countdown to the Big Rip would begin in the minds of cosmologists, transforming our ultimate fate from a slow fade into a sudden, catastrophic tear in the canvas of existence. Yet the Big Rip is not our only alternative to a cold, silent end. There exists a classic and deeply compelling vision of a universe that turns back on itself, collapsing into a fiery seed of rebirth. This is the Big Crunch. For this dramatic reversal to occur, the cosmic scales must tip decisively. The relentless outward push of dark energy would need to be overpowered by the collective gravitational pull of everything in the universe, from the mightiest galaxy clusters to the faintest wisps of dark matter. This requires the total density of the cosmos to be above a specific critical value, a cosmic threshold where gravity's inward tug ultimately wins the long war against expansion. Imagine the expansion of space slowly grinding to a halt. The distant galaxies which have been fleeing from us for billions of years would appear to freeze in place. Then, ever so slowly, they would begin to move closer. At first, the collapse would be almost imperceptible, a gentle cosmic sigh. But as the universe condenses, gravity's grip intensifies. The pace of collapse would accelerate, pulling galaxies closer and closer together. The night sky would grow brighter and hotter as the background radiation of space is compressed and energized. Galaxies would begin to merge in violent, spectacular collisions, yet there would be no one left to witness them. The temperature of the entire universe would soar, first vaporizing planets and stars, then breaking apart atoms into a searing plasma of nuclei and electrons. Space itself would shrink, curving in on itself as it approaches a final, singular state of infinite density and temperature, a mirror image of the Big Bang in reverse. This ultimate collapse could be the end of everything, or it could be a cosmic reset button. Some theories suggest the universe might be capable of a phoenix-like rebirth, bouncing from the crunch into a new Big Bang, initiating a new cycle of expansion and creation. This idea of an oscillating universe offers a profound sense of cosmic symmetry, an endless rhythm of birth, death, and renewal. So why has this beautiful, cyclic vision fallen out of favor? The evidence points overwhelmingly in the opposite direction. Our most precise measurements of the cosmos, particularly the detailed map of the cosmic microwave background, reveal a universe that is geometrically flat. This means its density is almost exactly at the critical value, not above it. More damningly, the observed acceleration of the expansion tells us that a mysterious repulsive force, dark energy, is actively dominating gravity's pull. The data does not show a universe slowing down for a great reversal, but one racing apart faster with every passing moment. While the Big Crunch remains a powerful idea in our imagination, our universe seems to have chosen a different, more expansive path, leaving the classic cycle of collapse and rebirth as a haunting echo of a cosmos that might have been. Brain cosmology suggests that gravity's profound weakness is the biggest clue to its true nature. While the other fundamental forces are confined to the three-dimensional surface of our universe, gravity may be the only one that can reach beyond it, leaking out into the higher dimensional expanse known as the bulk. Think of our cosmos as a vast, three-dimensional sheet of paper floating within a much larger, unseen space. The electromagnetic force, the strong and weak nuclear forces, all operate like ink trapped on the surface of that paper. But gravity is different. It acts like a watermark that soaks through the page, its influence diffusing into the surrounding dimensions. This leakage would dilute gravity's strength, explaining why it is so unimaginably feebler than the other forces. A single fridge magnet can overpower the entire gravitational pull of the Earth, holding a note against the door. This simple idea redefines the very fabric of our reality, proposing that the universe we perceive is just a slice of a much grander, multidimensional structure. This concept also offers a radical new perspective on cosmic expansion. The relentless push we attribute to dark energy might not be an energy at all, but a dynamic effect of our brain's interaction with the bulk or with other parallel brains. Perhaps the bulk itself contains a form of energy that exerts a pressure on our membrane, stretching it from the outside. Or maybe our universe is slowly drifting toward another brain in the dark, and their mutual gravitational attraction, playing out across the higher dimensions, is manifesting as an accelerating expansion within our own space. In this framework, the fate of the cosmos is not written in a simple equation for dark energy, but in the complex, unseen geometry of a reality with more than three spatial dimensions. It transforms the mystery of the universe's expansion from a question of what is inside our space to a question of what is outside it. The relentless expansion of our cosmos might be driven by a law so fundamental we find it in a steaming cup of coffee. The second law of thermodynamics states that the entropy of the universe, its level of disorder, always increases. A hot cup left alone will always cool down, its heat dispersing into the room, moving from a state of concentrated order to a diffused, disordered state. This is the universe's ultimate arrow of time. Now apply this to the cosmos itself. The universe began in an incredibly hot, dense, and highly ordered state after the Big Bang. Ever since, it has been evolving toward a state of maximum entropy, the heat death we call the Big Freeze. But what if this cosmic slide into disorder is not just a consequence of expansion, but its very engine? Some physicists propose that the drive to maximize entropy is the primary force pushing the universe apart. Think of it like this: a gas expands to fill its container because that is the arrangement with the highest entropy, the most possible ways for its molecules to be arranged. In the same way, the universe itself could be expanding because a larger, more diffuse cosmos has an astronomically higher entropy than a small, dense one. The vacuum of space, with its vast emptiness, is a high-entropy environment. By creating more and more of this empty volume, the universe is simply following the most probable path toward its own ultimate disorder. This thermodynamic perspective reframes dark energy. It might not be a mysterious substance, but a thermodynamic force, a manifestation of the universe's relentless drive to maximize its entropy. This idea finds a stunningly elegant partner in the holographic principle. If our three-dimensional reality is a projection from a two-dimensional boundary, then the universe's information content is limited by the area of that cosmic surface. As the universe expands, the area of this boundary grows. A larger surface can store more information, and information is deeply intertwined with entropy. More possible states mean higher entropy, so the universe could be expanding to increase its information storage capacity, to create more cosmic hard drive space for all the quantum bits that define our reality. In this view, the acceleration we measure is the universe actively maximizing both its entropy and its information content. It is not being pushed by a ghostly energy, but is pulled toward its own statistically inevitable future of infinite possibility and ultimate stillness. The force shaping the cosmos may be nothing more than nature's unwavering preference for mess. This dizzying vision of an infinite multiverse creates a profound statistical nightmare. If every possible universe exists somewhere, from one where gravity is repulsive to another where dark energy is 1,000 times stronger, how can we possibly say anything is likely or unlikely? This is the cosmological measure problem, a philosophical quagmire that strikes at the very heart of making predictions in a cosmos without end. Imagine you're trying to count votes in an election, but the number of voters is infinite. How do you determine which candidate is winning? You might start counting, but you could always find another infinite cluster of voters who support the other side. In an eternally inflating multiverse, the problem is infinitely worse. With an unlimited number of bubble universes, there are not just many versions of our cosmos with a small dark energy, there are also an infinite number with a dark energy value 1 billion times larger. In the stark logic of infinity, both sets are equally large. So why do we observe a universe with such a peculiarly tiny amount? The measure problem asks how we assign a probability to our observations. Without a way to cut the infinite multiverse down to a finite, countable size, we cannot say that our universe is probable or improbable, it just is. This directly impacts how we interpret the value of dark energy. The anthropic argument relies on the idea that most habitable universes will have a specific, small value. But if we cannot define what most means in an infinite ensemble, the argument loses its statistical power. Some physicists see this as a fatal flaw for the entire multiverse hypothesis. If a theory cannot make testable predictions about what we should observe, is it even science, or is it just a metaphysical statement? The search for a solution has led to incredibly complex mathematical proposals, attempts to impose a cosmic census by counting universes in a specific order or within a certain causal patch. But every proposed measure seems to have a paradoxical or unsatisfying consequence. The cosmological measure problem is ultimately a warning from the edge of logic. It suggests that an infinite reality might be fundamentally incompatible with our finite minds and our deep-seated need to find meaning in probability. This line of reasoning is known as the anthropic principle, a concept that is as logical as it is unsettling. It begins with a simple, undeniable observation: we are here. The universe we measure has precisely the physical constants that allow for our existence. The weak version of the principle states this obvious fact: the conditions in our universe are necessarily compatible with conscious life because we are that life. It is a simple statement of selection bias. We could not possibly observe a universe that forbids our own existence. The strong anthropic principle takes a far more controversial leap. It suggests the laws of the universe must be such that they eventually allow for the emergence of conscious observers. This implies a kind of cosmic fine-tuning, a direction or purpose written into the fabric of reality itself. The principle's most powerful application is to the cosmological constant problem. As we have seen, the vacuum energy predicted by quantum theory is catastrophically large. Yet the value we observe is almost zero, a number so perfectly small it allows galaxies, stars, and planets to form. The anthropic argument offers a stark explanation. In the vast landscape of a multiverse where every constant is set by random chance, the overwhelming majority of universes will have a cosmological constant that is enormous. In those chaotic realms, space expands so violently that matter is ripped apart before it can ever coalesce. No stars ignite, no planets cool, no life ever stirs. But in an exceptionally rare subset of bubbles, by pure statistical luck, the cosmological constant is minuscule. We, of course, find ourselves in one of those rare habitable pockets. Our existence is not evidence of a finely tuned cosmos, but a simple consequence of our own presence. We are not special, we are just lucky. This logic feels compelling, almost inescapable. Yet it draws fierce criticism from many scientists who argue it is a philosophical surrender disguised as an explanation. The most common charge is that it is a post hoc justification, an argument made after the fact that explains everything but predicts nothing. A true scientific theory makes testable predictions that can be proven false. What prediction does the anthropic principle make? It seems to say only that we should observe a universe we can live in, which is precisely what we do observe. It retroactively accounts for the data without offering any way to verify its core premise, the existence of other universes. Detractors see it as a conversation stopper, a way to dismiss one of physics's greatest puzzles by saying it could not be any other way. Why search for a fundamental law governing dark energy if its value is just a random lottery ticket? This tension lies at the heart of modern cosmology, a battle between two worldviews, one that seeks a unique, elegant theory of everything, and another that accepts a messy, sprawling multiverse where our place is merely a statistical fluke. The anthropic principle does not solve the mystery of dark energy. It simply reframes it, forcing us to ask whether the ultimate answers lie in the laws of physics or in the sheer, staggering improbability of our own existence. String theory was meant to be the final theory of everything, a single elegant framework to unify gravity with the quantum world. Yet its greatest success may have been to unveil a cosmos of infinite variety, not perfect unity. The mathematics of string theory do not point to one unique universe, but to an almost unimaginable multitude of possible stable universes, a landscape of perhaps 10 to the power of 500 distinct vacuums. Each of these possible universes corresponds to a different way for the extra dimensions proposed by string theory to curl up and compactify, a process that effectively sets the dials for every fundamental constant of nature. The strength of gravity, the mass of an electron, and the crucial value of the cosmological constant are all frozen into place by this random geometric process. In this vast landscape, our universe is not special. It is simply one possible configuration among more possibilities than there are atoms in our entire observable universe. The tiny value of dark energy we measure is not a law, it is a local ordinance, a random selection from an endless cosmic catalogue. This landscape provides a concrete, mathematical foundation for the multiverse idea. It transforms the anthropic principle from a philosophical argument into a potential physical reality. We exist in this particular bubble not because the laws of physics demand it, but because this is one of the exceptionally rare bubbles where the constants allow for the formation of galaxies, stars, and planets. The landscape offers a neat, if humbling, solution to the cosmological constant problem, explaining the incredible fine-tuning as a simple consequence of our own existence in a habitable pocket. Yet this grand vision is mired in a fierce debate. If the theory predicts every possible universe, does it actually predict anything at all? Critics argue that a theory that allows for 10 to the power of 500 outcomes has lost its power to explain why our universe has the specific properties we see. Instead of a unique set of laws, we get a cosmic lottery. For some, this represents a deep truth about reality. For others, it signals a profound failure, an admission that our quest for a single, elegant theory of everything has reached a dead end. The central challenge remains one of testability. How can we ever prove the existence of these other universes forever beyond our observational horizon? Some hope that subtle imprints from collisions with other bubbles in the landscape might be found in the cosmic microwave background, a faint bruise from a long-ago encounter with a neighboring reality. For now, no such evidence has been found. The string theory landscape forces us to confront a difficult question. Are we discovering that the ultimate nature of reality is an infinite, untamable garden of forking paths? Or are we simply lost in the weeds of a beautiful but ultimately unverifiable mathematics? Gravity feels like the most fundamental force in the universe, the very hand that sculpts the cosmos. But what if it is all an illusion? A radical new paradigm suggests that gravity is not a fundamental force at all, but an emergent phenomenon. Think of temperature. A single molecule does not have a temperature. Temperature is a collective property that emerges from the chaotic motion of trillions of molecules. In the same way, physicist Eric Verland proposes that gravity emerges from something even more fundamental, the information content of space-time itself. His theory of entropic gravity paints a picture where the force we feel is a consequence of the universe's relentless drive toward disorder. Imagine the fabric of space-time as being made of microscopic, indivisible bits of information like the pixels on a screen. When a massive object like a star sits within this fabric, it displaces these information bits, changing the entropy or the number of possible arrangements of the surrounding space. The apparent pull of gravity, according to this view, is not a force transmitted between bodies but a statistical tendency. Matter moves toward regions of higher entropy, much like a rubber ball drifts to a stop on the floor, not because of a direct force, but because that is the state with the most possible microscopic configurations. This single shift in perspective has breathtaking consequences. It can naturally explain the bizarre rotation of galaxies without needing any dark matter. The observed extra gravity that holds fast-moving stars in their orbits emerges directly from the entropy changes associated with the visible matter alone. The dark matter halo would be a phantom, a mirage created by our misunderstanding of how gravity truly works on cosmic scales. Even more profound is the theory's implication for dark energy. If gravity is entropic, then the acceleration of the universe is not driven by a mysterious substance. It emerges from the evolution of the cosmic information budget. As the universe expands, the total information content and entropy of the cosmos increase. The acceleration we measure could be the natural, thermodynamic response of a system maximizing its disorder, a cosmic expression of the second law. This turns our standard model on its head. Dark energy and dark matter are no longer invisible entities we must hunt for, but potential artifacts of treating an emergent force as a fundamental one. The universe is not filled with ghosts. We have simply been misreading the language of space-time. This idea is still in its infancy, fiercely debated and not yet proven. But it represents a profound philosophical shift, suggesting that the deepest layer of reality is not made of forces or particles, but of information. The force that binds us to the Earth might be the universe's most convincing hologram. The universe's first moments were shaped by a violence that makes dark energy seem placid. This was cosmic inflation, a burst of hyper-expansion that stretched a subatomic patch of space into a macroscopic cosmos in a fraction of a second. The engine for this explosive beginning is theorized to be a scalar field, the inflaton, which flooded the young universe with a repulsive gravity so potent it temporarily overwhelmed all other forces. Then, just as suddenly, the inflaton field decayed, its immense energy converting into the hot soup of particles that would eventually become us. But what became of the field itself? Could the same fundamental mechanism that launched the cosmos also be responsible for its final act? Some cosmologists see a profound link between the universe's first breath and its last gasp. They propose that the inflattened field did not simply vanish, but that its remnant, or a similar kind of field, is what we now call dark energy. In this unified picture, the inflattened field of the past could have slowly evolved into the quintessence field of the present. The same type of cosmic actor plays two different roles in the same grand play. The early universe required an immense push to smooth and flatten it, a job done by the inflatten. The modern universe needs a far gentler, more persistent push to explain the acceleration we see, a role perfectly suited for a faded, evolved version of that same field. This elegant idea connects the two most dramatic periods of expansion across the entire history of existence. Yet this beautiful symmetry faces a staggering problem of scale. The energy density that drove primordial inflation was colossal, while the energy density of dark energy is almost vanishingly small. Bridging this gap is the ultimate theoretical challenge. How does a force of such unimaginable power transform into the faintest whisper of a push? The answer might lie in the field's journey. As the universe expanded and cooled, the inflattened field could have rolled down its energy landscape, getting trapped in a shallow valley where its energy is minuscule but persistent. This would mean that the dark energy we measure today is not a new entity, but the final, faded echo of the very bang that started it all. It's a story where the end is written in the language of the beginning, a cosmic symmetry that ties our ultimate fate directly to our origin. This apparent balance in our cosmic era is profoundly strange, a puzzle known as the cosmological coincidence problem. Right now, the energy density of dark energy and the combined density of all matter in the universe are remarkably close to each other. We live in the one sliver of cosmic time where these two titans are in a near tie. This is an incredible fluke because these two densities change in completely different ways as the universe expands. The density of matter, both normal and dark, thins out dramatically. As space stretches, matter gets more and more spread out, like a drop of ink in a growing ocean. Its density drops fast. Dark energy, if it is a cosmological constant, is utterly different. Its energy density is a property of space itself. When you create new space, you create more dark energy. So its overall density remains constant, a relentless, unchanging push. For most of cosmic history, matter was completely dominant, its dense grip controlling the expansion. And in the far future, dark energy will be the unquestioned master, with matter diluted into irrelevance. The fact that we exist precisely during the brief crossover period, when the two are within an order of magnitude of each other, feels too convenient. It is as if you walked into a room just as a spinning coin landed perfectly on its edge. Why now? Are we just astronomically lucky to be born at this special moment? This question has led physicists to propose that dark energy is not a passive constant, but an active participant that has somehow locked onto matter's density. This is the idea behind tracker quintessence fields. Imagine a sophisticated predator tracking its prey through a forest, matching its pace and movements. A tracker field is designed to do something similar. In the early universe, when matter was very dense, the quintessence field would have adjusted its own energy density to mimic matter, following its lead and remaining subdominant. Then, as the universe expanded and matter's density fell below a certain threshold, the field would have undergone a transition. It would have broken from its tracking behavior and stabilized, turning into the dominant dark energy we see today. In this clever model, the coincidence is not a coincidence at all. It is a built-in feature of the physics. The field was always destined to catch up to matter and overtake it, making the current epoch a predictable phase in cosmic evolution, not a random accident. This elegant solution reframes our place in time. We are not living in a uniquely special now, but simply at the moment when a cosmic clock set at the beginning finally went off. Our entire cosmic neighborhood might be an astronomical backwater, The void hypothesis proposes a radical alternative to dark energy, suggesting we are not living in a representative part of the universe, but in a vast, underdense bubble. Imagine our local supercluster of galaxies is like a town in a secluded valley, while the rest of the cosmos is a sprawling, densely packed metropolis. According to Einstein's theory of gravity, the dense walls of matter surrounding our cosmic void would exert a stronger gravitational pull on us than the sparse region we inhabit. This imbalance would create a net effect, a gravitational tug that pulls our region outward, making it appear as if the entire universe is accelerating apart. In this scenario, the dimming of distant supernova is not due to a mysterious dark energy, but a simple consequence of our lopsided location. We are not being pushed from within, we are being pulled from without. This idea offers a beautifully simple solution, eliminating the need for any new, exotic substance. For it to work, however, the void would need to be staggeringly large, nearly 1 billion light-years across, with our galaxy sitting almost perfectly at its center. This requirement of a special location, a modern form of a geocentric universe, is deeply unsettling to many cosmologists who hold to the Copernican principle, the idea that our place in the cosmos is in no way privileged. And that is precisely where the void hypothesis runs into trouble with the data. Detailed three-dimensional maps of the universe, pieced together from galaxy surveys, show that while there are indeed vast cosmic voids and filaments, there is no evidence for a void of the required size and emptiness with us at its center. A crucial test comes from the kinetic Sunyaev-Zeldovich effect, which measures the motion of distant galaxy clusters by studying subtle distortions in the cosmic microwave background radiation. These observations have consistently shown that clusters are moving in a way that matches the predictions of a universe uniformly filled with dark energy, not one being tugged by a giant, unseen wall of matter. The evidence points overwhelmingly to a cosmos that is, on the largest scales, smooth and homogeneous. We are not in a special void, we are in a typical part of a universe that is genuinely accelerating from within. The void hypothesis, for all its elegant simplicity, has been largely ruled out, forcing us to accept that the strange push of dark energy is a real feature of our entire reality, not just a trick of our local perspective. Our universe's expansion is described by beautifully simple equations that assume space is perfectly smooth, a featureless ocean on the grandest scale. Yet when we look up, we see a cosmos clumped into an intricate cosmic web, a labyrinth of galaxy clusters, vast filaments, and immense empty voids. The backreaction hypothesis asks a daring question: what if this intricate structure itself is secretly steering the expansion? The smooth equations we rely on are an average, but the real universe is lumpy, and gravity's pull in these dense regions could be changing the behavior of the whole system. As galaxies and clusters form, their immense gravitational binding energy creates a kind of negative pressure on the surrounding space-time. Think of the cosmos as a vast, breathing lung. When you exhale, your diaphragm contracts and pushes air out. In a similar, though far more subtle way, the constant gravitational collapse of matter into filaments and knots might be causing the overall universe to exhale just a little bit faster. This collective effect, a backreaction from the formation of structure, could potentially mimic the influence of a dark energy, creating the illusion of acceleration without any mysterious substance. The mathematics behind this is profoundly complex, treating the universe not as a simple fluid, but as a dynamic landscape where every valley and mountain of matter subtly alters the geometry of space itself. For this idea to fully explain the observed acceleration, the backreaction effect would need to be significant, a substantial correction to the smooth model. The debate in cosmology is fierce. Proponents see it as an elegant way to solve the dark energy puzzle using only known physics and the observed structure of the cosmos. They argue we have been averaging out the universe's wrinkles for too long, missing their cumulative power. skeptics counter that detailed calculations suggest the effect is simply too small, a minor ripple that cannot account for the powerful, relentless push we measure. The true answer likely lies in more sophisticated simulations and future maps of the large-scale structure. If back reaction is real, it would mean that the fate of the cosmos is woven into the cosmic web itself, a tapestry whose threads of gravity are pulling the universe apart from within. These ghostly particles are streaming through you right now, billions every second. Neutrinos are cosmic phantoms, so reluctant to interact with matter that they pass through entire planets as if they were empty space. Yet these elusive particles might hold a key to the universe's accelerating expansion. The connection begins with a strange quirk of quantum behavior. As neutrinos travel, they oscillate, shifting between three distinct flavors: electron, muon, and tau. This very act of transformation hints at a deeper link to the cosmos. Some theorists propose that these flavor-changing neutrinos are constantly interacting with a background field that permeates all of reality, a field they call the acceleron. Picture this acceleron field as an invisible cosmic fluid. As neutrinos swim through this fluid, their interaction with it could be generating a persistent negative pressure. This pressure would act as a universal repulsive force, pushing the fabric of spacetime apart. The mechanism becomes even more elegant with the idea of mass-varying neutrinos. In this stunning proposal, the mass of a neutrino is not a fixed number. Instead, it depends directly on the local density of the acceleron field. In the early universe, when matter was densely packed, the acceleron field would have been dense as well, giving neutrinos a relatively large mass. But as the cosmos expanded and thinned out, the density of the acceleron field would have decreased. In response, the mass of neutrinos would have dropped. This shifting mass scale creates a feedback loop that drives cosmic acceleration. The lowering neutrino mass injects energy into the acceleron field, which in turn strengthens its repulsive push, causing the universe to expand faster. It is a beautiful and profound connection, tying the behavior of the smallest, most ghostly particles directly to the largest scale dynamics of the entire cosmos. The hunt is now on to test this elegant idea. Next-generation neutrino experiments like the Deep Underground Neutrino Experiment, DUNE, are designed with extreme precision. By firing intense beams of neutrinos over long distances and meticulously measuring how they oscillate between flavors, these detectors could uncover subtle anomalies. Any deviation from the expected pattern of oscillations could be the first evidence of the acceleron field's influence, a whisper from the hidden engine of the universe. The answer to our cosmic fate may not lie in some distant galaxy, but in the fleeting dance of a particle that moves through us like a ghost. Supersymmetry offers a breathtakingly elegant mathematical fix for the vacuum energy catastrophe. This theory, a favored extension of the standard model of particle physics, proposes a profound new symmetry in nature. For every known particle, from the humble electron to the forceful quark, there exists a super partner. An electron would be paired with a theoretical selectron, a quark with a squark, and a photon with a photino. This cosmic doubling is not just for show. In the pristine, unbroken state of supersymmetry, the quantum contributions of every particle to the vacuum energy are perfectly mirrored by its super partner. Think of it like a perfectly balanced set of books. The positive energy entries from ordinary particles are exactly cancelled out by the negative energy entries from their super partners. The result is a beautiful, clean zero, a vacuum energy that vanishes entirely. This would solve the cosmological constant problem in one stroke, explaining why empty space does not have the colossal repulsive push our calculations suggest. Yet nature, it seems, has no patience for perfect symmetry. If supersymmetry were unbroken, we would have detected these partner particles long ago. They would have the same mass as their familiar counterparts. The fact that we have not found them means that if supersymmetry is real, it must be a broken symmetry. the super partners are too heavy for our current colliders to produce. And this breaking of the symmetry shatters the perfect cancellation. The books are thrown out of balance, the positive and negative entries no longer match, leaving behind a remnant of vacuum energy. The problem is, this leftover is still astronomically larger than the tiny sliver of dark energy we actually observe. So while supersymmetry points toward a beautiful mechanism for a zero cosmological constant, the broken reality of our universe leaves us with a puzzle that is just as deep. The theory shows us a path to perfection, only to highlight how far our own cosmos has strayed from it. For decades, we have been building theories in the dark. All these grand ideas, from phantom energy to cosmic holograms, remain trapped on the chalkboard until they can be tested against the cold, hard light of the stars. That long wait is almost over. The next generation of cosmic observatories is poised to turn speculation into science, and their findings could shatter our current understanding of the universe. Leading this charge is the Vera C. Rubin Observatory in Chile, a facility with a camera so powerful it could photograph a golf ball from 15,000 miles away. Over 10 years, it will conduct the legacy survey of space and time, scanning the entire southern sky every few nights. It will not just find millions of new galaxies, it will watch them, creating the first ever motion picture of the cosmos. By tracking how the vast cosmic web of galaxies stretches and evolves over billions of years, the survey will measure the expansion history of the universe with a precision we can only dream of today. This immense map will reveal the subtle competition between dark energy and gravity playing out across the largest possible stage. Joining this effort from the pristine vantage of space is the Nancy Grace Roman Space Telescope. Often called Hubble's wide-eyed cousin, Roman will combine a massive field of view with the sharp vision of a space telescope. It will perform its own giant galactic survey, but its unique power lies in peering back to the cosmic dawn, observing the very first moments when dark energy began to dominate the universe. Roman will use a phenomenon called weak gravitational lensing, where the light from distant galaxies is warped by the invisible dark matter that lies in between. By mapping this distortion with exquisite detail, the telescope will trace the distribution of both dark matter and dark energy, revealing how they have shaped the cosmos over time. Meanwhile, the European Space Agency's Euclid spacecraft is already on its mission to chart the geometry of the dark universe. Euclid specializes in measuring the slight bending of light with a level of accuracy never before achieved. It will construct a three-dimensional map of the universe spanning 10 billion light-years. The true power of these missions lies in their combined, relentless data collection. They are not designed to find a single smoking gun, but to measure a single number with excruciating precision, the equation of state parameter for dark energy, denoted as W. This one value is the key that unlocks the mystery. If W is exactly -1, it confirms the simplest idea, Einstein's cosmological constant, a steady, unchanging vacuum energy. If W is even slightly greater than -1, it points toward a dynamic field like Quintessence that is slowly fading. And if it is less than -1, the universe is set on a course for the catastrophic Big Rip. The measurements from Rubin, Roman, and Euclid will shrink the error bars on W so dramatically that they could definitively rule out entire classes of theories. The elegant Chaplain gas, the terrifying phantom energy, and many models of modified gravity have clear predictions for what W should be. If the data does not match, those ideas will be relegated to the history of physics. We are standing at the edge of a revolution in cosmology. The next decade of observation will not just add another piece to the puzzle, it will determine the shape of the puzzle itself, telling us which of our 30 theories are beautiful fantasies and which are the true architecture of reality. The silent cosmos is now speaking to us through ripples in spacetime itself. gravitational waves, first detected less than a decade ago, have opened a brand new window on the universe, and they may hold the key to unlocking the mystery of dark energy. Every time two massive objects like neutron stars or black holes spiral into each other and merge, they send out a powerful tremor that travels at the speed of light, warping the very fabric of reality. These cataclysmic events are more than just cosmic spectacles. They are what astronomers call standard sirens. Think of a standard siren like a fire truck with its siren blaring. As the truck moves away from you, the sound waves stretch out and the pitch of the siren drops. You can calculate exactly how fast the truck is moving just by listening to that change in pitch. Gravitational waves work in the same way. By analyzing the specific waveform of the merger, scientists can calculate the true, intrinsic brightness of the event, how powerful the cosmic siren really is. Then, by measuring how much the waves have been stretched or red-shifted by the expansion of the universe, they can determine the distance to the collision with incredible precision. This gives us a completely independent yardstick for measuring cosmic distances, one that does not rely on the traditional ladder of methods involving stars and galaxies. This is crucial because every potential source of error in our current measurements of dark energy comes from that old cosmic distance ladder. Gravitational waves cut the ladder away entirely. As our detectors like LIGO and Virgo become more sensitive, they will build up a vast catalog of these standard sirens from different eras in cosmic history. The future LISA mission, a space-based observatory, will detect the mergers of supermassive black holes, events so powerful they can be seen from the dawn of time. By plotting the distances and redshifts of thousands of these events, we will trace the expansion history of the universe with a clarity we have never had before. We will see exactly how the push of dark energy has changed over billions of years. Does it hold steady like a cosmological constant, or does it ebb and flow like a quintessence field? The data from these cosmic messengers will provide a definitive answer, placing powerful new constraints that could validate one of our 30 theories and rule out dozens of others. The whispers of colliding black holes might finally tell us what force is writing the final chapter of our universe. These 30 theories reveal a cosmos of staggering possibility, yet they all share a single, silent boundary. Our current physics has two magnificent pillars, general relativity and quantum mechanics, and they speak entirely different languages about reality. One describes the cosmic stage of spacetime with beautiful, smooth curves, while the other describes the frantic quantum actors upon it with probabilities and uncertainties. Dark energy sits squarely in the chasm between them, a phenomenon that demands we understand how gravity works on the quantum scale. We are trying to solve a puzzle without the final piece of the box, a unified theory of quantum gravity. This missing framework is the holy grail of modern physics, and without it, our explanations for the cosmos's acceleration may be like using Newtonian mechanics to describe a black hole, a useful approximation that breaks down at the edge of truth. String theory and loop quantum gravity are valiant attempts to build this bridge, but so far they remain largely untested mathematical landscapes. The profound question then becomes, are we simply missing the next great breakthrough, or are some truths about the universe fundamentally inaccessible to a human mind evolved to navigate a three-dimensional world? Our brains are pattern recognition engines fine-tuned for survival on a single planet, not for intuitively grasping higher dimensions or the quantum nature of a vacuum. The ultimate explanation for dark energy might be as incomprehensible to us as a smartphone would be to a cave painter, yet history offers a humbling counterpoint. Every time we have believed we have reached the limits of understanding, a Copernicus, a Newton, or an Einstein has emerged to shatter our assumptions and reveal a deeper, more elegant layer of reality. We stand at that same precipice today. The mystery of the expanding universe is not just a question about our fate. It is an invitation to the next great revolution, one that will not only tell us why space is stretching, but will ultimately reveal what space itself truly is. We have journeyed through 30 mind-expanding theories, from the steady push of Einstein's cosmological constant to the terrifying phantom energy that could rip reality apart, from the elegant simplification of the Chaplin gas to the radical idea that gravity itself is an illusion. We have explored cosmic holograms, cyclic universes, and the possibility that our entire reality is just one bubble in an infinite multiverse. The sheer breadth of these ideas reveals a profound truth: we still do not know what dark energy is. This vast ocean of unanswered questions is not a sign of failure, but a beacon. It marks this as one of the most thrilling frontiers in all of human knowledge. The ultimate solution will probably not be a single theory from our list, but a breathtaking synthesis of several, or perhaps a concept so radical we have not yet found the words to describe it. It will be a framework that seamlessly weaves together the quantum world with the cosmos, finally explaining the silent force that is writing our cosmic destiny. This journey does not end here. It continues with every new observation, every new telescope, and every new idea. Now we turn the question to you: which of these 30 theories resonates most deeply with your vision of reality? Does the cyclic universe speak to you, or does the holographic principle fire your imagination? Let us know your favorite in the comments below. If you enjoyed this deep dive into the greatest mystery of our time, please give the video a like. It truly helps us continue exploring these cosmic questions. And be sure to subscribe so you do not miss our next adventure to the very edge of physics.